Hi, welcome to my virtual VSS talk. Thanks so much for stopping by. Here I'd like to present to you a project called Context Information Supports Serial Dependence of Multiple Visual Objects Across Memory Episodes. It's work I've been doing together with my supervisor, Christoph Glidowski, and my other great collaborators, Stefan Zoschke, Benjamin Peters, Benjamin Rahm, and Jochen Kaiser. We recently published this work, so if you'd prefer to read the paper, you can of course do that, but if you'd like to listen, just stick along. To start, I'd like to give you a short introduction into what serial dependence actually is. In everyday life, or in working memory experiments, we are confronted with memory episodes, and in those we might encounter objects that could look like this, and then we might have to do something with this object, like keeping it in mind for a little while and then recalling it. And then the memory episode is over and the next one starts, and there we might encounter a quite similar looking object. And recently it has been shown that the previous episode is affecting the processing in the current episode, in a way that the current object appears to be more similar to the previous object than it actually is. This systematic bias has been called serial dependence and was first demonstrated by Jason Fisher and David Whitney. In their experiment, participants had to remember the orientation of a Gabor patch, and then after a short delay, recall that orientation by adjusting a randomly oriented line. In the next trial, they had to do exactly the same thing with a differently oriented Gabor. And then they could observe that the current orientation is affected by the previous orientation, in a way that the current report is attracted towards the previous orientation. This attractive bias follows the stereotypical tuning curve you can see here, and it basically just tells us that only items that are sufficiently similar to one another will be attracted over time. Since then, serial dependence has been demonstrated in a variety of modalities, like faces, spatial positions, and motion directions. And furthermore, it has been shown that serial dependence most strongly operates between items that are spatially and temporally close to one another. Based on those characteristics, it has been hypothesized that serial dependence could be reflecting a beneficial mechanism that smooths visual inputs over time and thereby helps us to create the impression of a stable and coherent environment. Based on that, we thought to ourselves, okay, then how should serial dependence operate if there are multiple objects present within each episode? It wouldn't really be beneficial if, for example, this left object is biased equally towards all the objects of the previous episode. Rather, we would expect that serial dependence operates object selective. For that, we need some guidance about which item reflects the same object over time. Object identity could, for example, be indicated by spatial position of the items. Then, for example, we would expect that this left object is biased more towards the previous left object than the previous right object. Object identity could as well be indicated by item color, so then we would expect that the current green object is biased more towards the previous green than the previous red object. Or object identity could be indicated by temporal position within an episode. In a set of 4 experiments, we investigated if those accompanying object features can help to relate objects over time and thereby support serial dependence. In the first 2 experiments, we sequentially presented 2 motion directions per trial, and the motion directions were displayed by coherently moving dots that could be colored red or green. After a short delay, participants were retrocued to recall one of the 2 items, and then had to recall the motion direction by adjusting a randomly oriented line. If we take a closer look at one of the items in this example trial, we can look at the item at the object level or further disintegrate it into its single features. And then we can differentiate between the content feature of an item, in our case motion direction because participants had to remember and recall that feature, and the so-called context features, which are accompanying discriminative object features, in our case color and serial position. As you could see in the previous slide, the participants were cued in the first experiment by color about which motion direction to recall. Thereby, color was a task-relevant context feature, and serial position was completely task-irrelevant. To investigate the role of task relevance, we mixed that up in the second experiment. There, we cued via serial position, and we further allowed 2 items within a trial to have the same or different colors. Thereby, serial position was task-relevant, and color completely task-irrelevant. And you can further characterize an item by whether it was a target in the current trial or a non-target. Based on that, we could investigate how serial dependence is affected by different factors. So first, we could investigate how context features affect serial dependence by comparing serial dependence between items with the same colors versus items with the different colors, and by comparing serial dependence between items with the same serial positions versus those with different serial positions. And furthermore, we could investigate the role of selection in working memory for serial dependence by comparing serial dependence toward previous targets versus previous non-targets. So here you see again a quick overview over our methods for the first two experiments. As I told you in the first experiment, we cued the target item via color, and in the second experiment via its serial position. And participants had to come in for 2 sessions at 2 hours, which gave us quite a bit of trials for each participant. To analyze the data, we looked at each motion direction that had to be recalled and put it into relation to a previous motion direction. Then we looked at the response error a participant made and ordered those response errors by inter-item differences, which are denoted here at the x-axis. Then, for each inter-item difference and each participant, we averaged the response errors that would then end up as one of the blue dots you can see here. And if there's no response bias, you would expect that the blue dots would fluctuate randomly around 0. But as you can already see, they are systematically shifted in a direction that indicates attraction. To better describe the bias, we fit a derivative of Gaussian, which is commonly used in serial dependent studies, and you can see here as the black curve. And it gives you the advantage to describe the bias with 2 parameters, namely the amplitude, which indicates the strength of the bias, and the width, which indicates the tuning width or selectivity of the bias. The significance of such model fits was then assessed by permutation tests against 0, and to compare conditions to one another, we used permutation tests between model fits of those different conditions. So let's start with our results. Generally speaking, across all our 4 experiments, we observed serial dependence, even though we presented 2 items per trial instead of what is commonly used in serial dependent studies, 1 item per trial. In our first experiment, where color was the task-relevant context feature, we indeed saw that color affected serial dependence, in a way that serial dependence between items with the same color, shown here as the dark turquoise curve, had a stronger and more broadly tuned bias than items with different colors. The task-relevant context feature serial position, in contrast, showed no effect on the amplitude of serial dependence, but it affected the width of the bias, so that items with the same serial position across trials had a broader tuned serial dependence between them. And we could only observe a significant bias towards previous targets and a non-significant bias towards previous non-targets. But the bias towards previous non-targets only fell short of significance with a p-value around 0.06. Therefore, in our second experiment, we drastically increased the sample size to see if anything is going on with the non-target. But let's first start again with our color context feature. In experiment 2, it was task-relevant, and it did not affect either amplitude or width of serial dependence. In contrast, serial position, which was now the task-relevant context feature, affected both the amplitude and the width of the bias. And, indeed, with a higher sample size, we saw that there is a significant bias towards the previous non-target, which was crucially smaller than the bias towards the previous target. In our second set of experiments, we exchanged the context feature of serial position with spatial position, which is of course an important object feature and often used in visual working memory experiments. Therefore, we presented the motion directions simultaneously instead of sequentially. The only other difference to the first 2 experiments was that we increased the encoding and masking times accordingly. Other than that, it was exactly the same. So in the third experiment, again we cued via color, and in the fourth experiment via spatial position. So let's continue with the results for our second set of experiments. In experiment 3, where again color was the task-relevant context feature, we saw that color affected serial dependence, thereby replicating the results of experiment 1. And this time, we even saw a stronger effect, as we could only observe a significant serial dependence between items with the same colors and not with different colors. Then, for the task-relevant context feature spatial position, we saw that it too affected serial dependence crucially, in a way that we could only see a significant serial dependence between items with the same spatial positions, and no significant bias between items with different spatial positions. And the familiar picture, we could only see significant serial dependence toward previous targets. In our final experiment, in which we cued via spatial position, we could again observe that task-relevant color had no effect on serial dependence. In contrast, task-relevant spatial position had a strong effect on serial dependence, as we could again observe only a significant bias between items with the same spatial position across trials. And, once again, we observed that there is only a significant serial dependence towards previous targets. This set of results leads us to the following conclusions. First, content-context bindings persist across memory episodes and can affect the processing in the current episode. Second, context features do indeed support serial dependence, especially when those context features were task relevant. And finally, we could mainly observe serial dependence toward previous targets. Taken together, we think that those results support the interpretation that serial dependence could be a beneficial mechanism. But of course, more research has to be done on that in the future. With that, I'd like to thank you for your attention. Please contact us if you have any questions or comments, and then hopefully I see you next year in Florida.